some water? And if you want some water.
Yeah,
here.
Great.
We take care of our speakers.
So this is the time.
You'll also have someone right there showing
Yeah,
you
but
when you
I
have
want
15
to
minutes
know
left.
if I'm keeping the pace.
So you have 30 minutes, and then we have 5 more minutes for Q&A.
Okay, so 35 in total?
No. 30 minutes, and then 5 minutes for Q&A. So 35 total.
Okay,
Yeah.
fine. Whoops.
It's going to be interesting.
All right, so we still have 9 minutes, so yeah, we have time.
Do you want anything? All right. So I will bring it when I.
Do you need us to save your seat? No.
Okay, so if you have spaces in between the rows, please move towards the center so we can see easier. Also, if you have a space next to you, please raise your hand. Oh, there's more. If you have an empty space next to you, raise your hand. I know there's empty spaces there. Thank you. All right, so please try to sit down as soon as possible so we can see how many more people we can fit. Where's the we have. So there's 2 spaces there. So if you want to sit there, yeah. I just want to. How many empty spaces are in the back? Like, 6.
I'll be your timer.
Thanks. Will you please help me? Will you please help me with this one because I'm not able. Okay. I will keep a timer for me too, just to not acknowledge that I'm halfway where I'm still at the slide. And thanks.
Okay, one more place on there. Any more empty seats? One more. Okay, wait. Any more empty seats? Oh yeah. That's fine. Cool. So for the rest, if you want us to end up there, I'm okay with it. But you can feel that. So go to the end. That's better, but I mean, like, they have a different. Keep going towards the end, please. Do not block the way. Keep going towards the end. No, but I mean, like, go towards the end. I don't know where these people are. Actually, more. You can have like CD. I'll find out. Yeah.
Immagina fuori il proiettore.
Yeah, so if you're going to be there, you're going to be the only one on the live stream. So that's fine. Cool, so we'll start in 6 minutes because live stream and recording and all that stuff. So we need to wait.
Shall I tell a few jokes? Well, so how about that one that If it's on Jupyter, it's data science. If it's on code, it's machine learning. If it's on PowerPoint, it's artificial intelligence.
Why did the ML algorithm jump off the bridge? Why did the ML algorithm jump it off the bridge? Because everybody was doing it.
So, your colleague said why the machine learning model jumped off the bridge, because all his friends was doing it.
This is everything he's saying is already recorded forever. So
That's actually the nice part.
I have a very bad one. What is the favorite programming language of pirates?
Off?
Of pirates. Arr. Yeah. Any other bad jokes? Or good ones, too.
Yes.
That's harder, but.
Machine learning algorithm walks into a bar. The bartender says, "What will you have?" And he says, "What's everyone else have?"
Kind of nice variation of why it jumped off the bridge.
Well, what does Bruce Lee says when he's thirsty? What the heck?
That was off topic. How many of you are acquainted with neural networks? So I get the risk of being really misinterpreted. Okay, no, really, some survey just to let me know which things I should actually run faster and which one I should actually explain a little better. So raise your hand if you're already acquainted with neural networks. Good. Raise your hand if you're already acquainted with the machine translation problems. Very nice. Okay, great. That was useful. Three more minutes. The anticipation is killing. So a nice joke, and this is real. Actually, this presentation should have had a very, very different tone, because when I tried to run the experiment totally failed. And so I was about of doing a presentation about, well, we failed, but we learned a lot of nice stuff. Fuck. And it's still there. If you have a hand shift, okay. Yeah, I think so. And so,
Your phone is talking to you.
and so basically, it was a kind of a history of, okay, we failed, but why we failed. So there's this, and this problem. And instead, yesterday evening, I basically had a revelation, and I set up the experiment with a different parameter, which I was not thinking, and the experiment was a total success. So I had to rework my presentation on the fly, and then I said, okay, what if I just try to tier the model on very, very different subjects, and the experiment failed. So actually, we will have the best of both worlds.
Your battery is there.
Great.
Do you have your charger with you? Actually,
The charger, no?
Is
There's
the
a
one.
different one. I have my charger with me. I do have it.
Yeah, you have 13 seconds.
Guys, make way. So we will have a nice story about how we succeeded, and a nice story about how we failed, and so how the experiment is constrained. And so it will be very exciting.
All right, good. So we're on time. You ready?
Great.
No water on top. Okay, so round of applause.
Hello everybody, I'm Alberto Massidda, and today we are going to talk about teaching machines to read code changes and actually to tell what happened. So predicting a commit message with neural networks. Just a brief word, I want to thank my company who sent me here, provided all the hardware for the training, for running experiments, providing the time for me to run the experiments. And we basically are a consulting company completely devoted to open source, which is pretty cool. And we only use open source technology. And we are an Italian-based company. We do DevOps, cloud, ML, big data, and lots of interesting stuff. So, why would we want a commit message suggestion? And is this presentation actually? Seriously? Well, okay. Why do you want a commit message suggestion? For example, because we want to just help the developer, for example. So we want to give an aid to the developer. Or for example, we want to catch bad commit messages. Just imagine if your Jenkins pipeline was able to reject pull requests based on the lousy commit message that was attached. I think we all been there, right? So it would be nice if we had an automated way to generate stuff, to use it as similarity metrics and how good a commit message is. What we don't want, anyway, is a message based on templates, because message based on templates just suck. They can just tell you very, very narrow cases, and we don't want just a nice crafted message where you fill just names. Instead, we really generate a message which pertains the very specific case you're tackling. And we don't want also a message that summarizes what has changed, because what has changed is trivial. This file changed in this way. This is the point of the git patch, the git diff message itself. Instead, we want a message that captures the high, at least the medium level intents of the coder and why it changed. Okay? So it turns out that generating a message for a code change is a problem of summarization. And we want to generalize what was the intent of the coder, at least at a low level, why he did that. And maybe we are not exposed to the high level of the project because you cannot even tell it by looking at the commit history, but we want to know what is changing in that particular context. A change of code always comes with a commit message which describes the full change. So in essence, when the developer writes a commit message, it's generating a summary of the changes. And we want to exploit particularly this thing. A diff patch provides a really focused source of code to summary mapping. So in this case, we change only this line, and we replace with this, and this one is being copied because I want to generalize for multiple items. And so the point of the learning in this case is learning a code to summary mapping. What can we use for that? Neural networks. Neural networks are particularly good at generalizing mapping from source to target. And machine translation can actually help a lot, because the whole point of the statistical machine translation and later on neural machine translation nowadays is to infer a mapping between languages. And by means of counting the co-occurrences of words between two different parallel corpora, or vector embedding manipulation. What I mean is that if we take a sentence and we map it into a dense vector of float numbers, right? Much like we do with the TF-IDF in information retrieval thing. And we putting into a multidimensional space, in a high dimensional space, like 256 dimensions, concepts that will be really near will be near in this space. And this holds true across different languages. So we can map from a language to another by looking at vectors, at concepts that sits near in the language. So in order to do a machine translation, we need an architecture first and a data set. The architecture that we picked in this case is the Google Neural Machine Translation architecture, which is the state-of-the-art for the machine translation. Basically, this is a sequence-to-sequence model with attention. We have here the inputs and are fed into a bidirectional recurrent neural network with LSTM cell in order to prevent the vanishing gradient problem, which is the phenomenon by which the neural network tends to forget what is seen in a state which is far into the computation, and so it's not able to learn. Then we feed this double pass, forward and backward pass, to a stack of 8 layers, which have also residual connection. Residual connection is when you just, you not only feed the input of previous layers into the new one, but you also feed the original input and you concatenate together. This is because it was observed that producing the intermediate representation of a result along with the input helps generalizing better, because the gradients, when you are back propagating, flows across the residual connections and are not hampered, basically. Then you feed everything to an attention model, which is a nice machine that sits in between and helps understanding what is the part of the input that should be used across all the multiple words that you have been feeding in to generate the current state in a decoder. The decoder is the network on the right, which is the one which currently is really generating the sentences. Okay, so this one is getting the context of the diff patch, everything that has changed, the file names changed, the code changed, feeds into a decoder which generates, by means of a recurrent neural network, it generates the real words that will be fed. And also this one is a stacked 8-fold recurrent neural network with is monotonic, it's not bidirectional, with residual connections. And then we needed a data set. So we used the commit data set provided by the Jiang and Macmillan experiment, which this presentation takes inspiration from, which was a research done 2 years ago about how to extract commit messages from diff patches. They used a totally different technology because they didn't have this at the time, so we are actually using better weapons to tackle the same problem. It's 2 million commits from the top 1,000 Java repositories on GitHub. We extracted only the first sentences from each commit message. So and then we basically stripped away the issuer, the commit hash. We tokenized everything with white space, keeping the candle casing and punctuation because it's part of the language. And then we basically had to cut out everything which was longer than 100 words, being in diff patch or being in the commit message. And this left us with 75 commits. And then we apply another filter, which was described in that experiment of 2 years ago by Jiang Macmillan, which was try only keeping the verb direct object messages. So if I take a bad commit message like blobs of code that then fix, I cannot really, and there's lots of them, I cannot feed it to the as a training sample because it will make my model produce garbage. So the best commit messages are those which begin with a verb, added this file, updated the changelog, I don't know, removed this kind of import. And then there is a direct object after that. So it really is a good message that summarizes. It was a very heuristic way to tell bad commit messages from good one and try to have a kind of unsupervised way to separate bad messages which should never be fed as a training samples. And so we left with the 32,000 commits split in 3 different sets. The biggest for training, then one for validation during the one for testing during the training, and one for validation after the training was done to prevent peaking. We use the Sockeye, which is a deep learning framework for sequence to sequence, much like tensor to tensor, based on AWS MXNet, which is a really cool framework, by the way, even though it's really an underdog of the field. Everybody is just in love with PyTorch and TensorFlow. I like MXNet because it's really polished, they're really well designed from ground up. And the training happened of AWS itself over a Tesla K80 and a Tesla V100. And I want to spend a few words about the fact that the new GPU that NVIDIA released is a total beast. And it costs 4 times as much, but it's 4 times faster. So they say that the only thing that money can't buy is time. Well, in deep learning, this buys you a lot of time. And the original experiment was 38 hours training length. I ended up in 5 hours. So it really let me iterate a lot. And you can see that from the perplexity of the output generated during the training, you can see the model really picked up instantaneously. And there was no overfitting. This is the same graph over logarithmic scale. So you can see the model still has a long way in this apparently flat field here, and it's still really picking up, and it stopped by itself after entering that plateau. So the results 5 hours later, which is 242 epochs and 43,000 mini batches, are these. And these are actual figures I ripped out from yesterday evening while I was frantically scrapping through my presentation to tweak it. So I removed these 2 lines. This is the human, their original commit on the validation set, so no peaking here. So remove no needed imports. The machine translation said remove unused import. So the machine really generate this message just looking at this one. And in this case, the messages are actually equal. So add the table of contents in Python README, and the machine said really the same. So this makes me think there's a kind of a repetition pattern in the training data. The training data was shuffled and was divided. So it should be really, I could not believe it like this, because I thought the machine would have tweaked it a little. And this one is nice. Here we are updating the version of Gradle, and so update Gradle. And the machine said update the build tools version. So he knows that Gradle is a build tool, and he understood that I was updating the version actually. This is my favorite. So version 1.2.3 in the POM file of Maven plugin. Update the OS Maven plugin to fix an issue with IntelliJ IDEA on Windows. There was no way the machine could actually know that on Windows the developer had a problem. And so the machine said, upgrade the OS Maven plugin to fix the build issue. Because if you're fixing the POM file, it means that you have a build issue. And this is the actual plot of the neurons in the attention model. So, okay, let me just go through this. Here you can see the patch, the commit message. So it's everything like this, crammed in just one line, okay? And you can see here the message that was output, upgrade OS Maven plugin to fix the build issue. It's really crammed because this is a fixed representation graph, and so the labels jump one another. And here you can see that these are the neurons who got activated. So whenever you see blank space, you actually are seeing neurons that didn't fire up. So it's a matrix multiplication. So if you multiply your input in a matrix, you obtain another matrix as an output, or you obtain an output field. And so the neurons who actually have the highest score, they have activated, okay? Like this standard neural network stuff. And the neurons who have a low score actually didn't fire up. This is because there was no matching, like a template, between the input and the output, like the input vector running over the matrix, okay? So here we are plotting the real float numbers in a grayscale. So the higher the numbers, the higher the correlation between this input and this output here. So you can see the upgrade OS Maven actually triggered when it saw artifact ID words and it saw Maven. And here, to fix the build issue, triggered a lot when he saw Maven. So Maven is a synonym for build issue, because if you're changing your POM file, it means that you have a serious problem building up. That's what the machine learned, actually. And the graph goes this way, because you start from the first word, which are the top right there, and here. So the gradients falls like this. So was everything actually a success? Well, for those who are not acquainted with machine translation lingo, the metric that we use in machine translation is called BLEU, which is a bilingual evaluation. I don't remember what it is, but the fact is that we actually compare the output of machine translation and a human translation, and we count the n-grams, the words in common between the original and this one. It's scaled between 0 and...
Anything it hasn't seen in the training set? Would it be possible to make it point to specific inputs that it maybe hasn't seen before?
Okay, so the question was, since you are actually trying to learning to translate between something that you've seen, right? How can you actually cope with things that you haven't seen? Well, that's the problem of out-of-vocabulary words. And neural machine translation suffers a lot from this because it's not able to generate a float vector of something it hasn't seen. So there is an effort is factorizing the words into subwords, and so that you can cope with n-grams. But generally, it does a good job because we use frameworks. So there's a lot of stuff which is in common different projects. And this tells us about the nature of software development, in which most of the code is not ours, but it's of the framework. And there are conventions, naming conventions, which helps a little. And otherwise, you get a rubbish thing which is not able to compute. But most of the times it goes well. And the very high BLEU score is very encouraging.
Okay, so time's up for questions. Thank you very much, Roberto.
Thank you, so.
The mic?
Yep.
Now we have
Very cool, thanks. Thank you.
Thank you so much. Very, very nice.
Oh, I was shitless scared when I spilled the water on my
I know.
laptop.
I would turn it off just in case, like, and
Yep.
make sure to